You know how your phone just seems to get you, like it knows you're a cat person? Or how Netflix will serve up a movie that you actually end up loving? Well, that's not magic, right? It's all about data, but not just the numbery kind. We're going to dive into how computers learn to understand our messy, human world, a world filled with things like cats, dogs, and, well, everything in between.
I mean, it seems so simple to us, doesn't it? A cat is a cat, a dog is a dog. End of story. But for a computer, that's a massive challenge. Think about it. How do you explain the difference between a fluffy Persian cat and a sleek Siamese, or a giant Great Dane and a little corgi, using only math? That is the core puzzle we're going to unpack today.
Okay, so picture this. You're at your favorite coffee shop. The price of your latte, let's say $4.50, that's numerical data. Easy peasy. But the type of milk you pick, oat, soy, whole milk, that's what we call categorical data. See, it's not a number, it's a label, a distinct choice from a list. And for machine learning, that difference, well, that's where things get really, really interesting. So here's the fundamental problem. Machine learning models, deep down, only speak one language, and that language is numbers, specifically floating point numbers. It's like trying to explain the color blue to someone who's only ever seen it in black and white. You can't just say, it's blue. You have to find a way to describe it in terms they get. And that's our job. We have to be the expert translators, turning our world of words and labels into their native tongue of numbers. So how do we actually do that? How do we become these expert translators? Well, that's what we're here to figure out. First, we're going to uncover how to translate our world for computers. Then we'll look at what happens when those translations go wrong, which, trust me, they do. And finally, we'll get into a really cool trick that helps them understand not just the words, but the deeper meaning behind them.
All right, first up, the computer's language problem. Let's just dive right in.
The secret sauce, the thing that bridges this gap, is a process called encoding. You can think of it as the magic trick that turns all those words and labels into numerical vectors that a machine can actually understand. And I'm not kidding when I say this is fundamental. Without encoding, you wouldn't have recommendation engines, self-driving cars, or even spam filters. It's the foundation for so much of the AI we use every day.
So, okay, we know we need to encode things. But how? Well, let's look at one of the most common and, honestly, most elegant ways to do it. It's a technique called One-Hot Encoding, and it's pretty much a universal translator.
It's a simple three-step process. First, you just identify all the unique categories you have. So if we're talking about t-shirts, this would be red, blue, green. That's your vocabulary. Second, you give each of those categories its own unique number, like an index. So red is 0, blue is 1, green is 2. But, and this is the important part, we can't just stop there. We don't want the computer thinking green, 2, is somehow more or better than red, 0. So that brings us to the third and most clever step, creating a special vector for each one. And here's what that looks like. Let's take car colors. For each color, we create this list of zeros, basically a bank of light switches that are all off. For red, we flip the first switch to a 1. Everything else stays 0. For orange, we flipped the second switch to 1. See what's happening? Each category gets its own unique on switch. It's a super simple but brilliant way to tell the model, hey, these things are all distinct and separate. Now, this might seem like a really technical detail, but it is absolutely crucial. What this vector does is tell the model that these categories are different, but it doesn't imply that one is bigger or better than another. There's no accidental ranking. Red isn't less than orange. They're just different. We're preventing the model from making a totally false assumption based on the numbers we assign. Okay, so we've got our translation method down, we're feeling good, but there's the catch. Your translation is only ever as good as your dictionary. This brings us to the idea of gold labels versus silver labels. Let's break this down. Gold labels are basically human-labeled data. Think of it like a beautiful, handcrafted piece of furniture. The quality is amazing, it's precise, but man, it takes a ton of time and effort. Silver labels, on the other hand, are machine-labeled. They're like that flat-pack furniture you get from a big box store. You can get a lot of it fast and it does the job, but the quality can be a little shaky. It's all about a trade-off between quality and scale. But here's the thing, even those gold human labels aren't perfect. I mean, humans make mistakes, right? We get tired, we have our own biases, and sometimes we just flat out disagree. You ask two people if a movie review is positive or negative, and you might get two different answers. That disagreement between raters is a real problem you have to account for. And then you've got the silver labels. This is where things can get, well, a little weird. There's this famous quote that just sums it up perfectly. If a computer vision model mislabels a photo of a chihuahua as a muffin, models trained on that labeled data will be of lower quality. And yeah, it's hilarious to think about, a chihuahua muffin model, but it highlights a super serious point. A machine might make a mistake that is just completely nonsensical to a human. So why does any of this matter? It really boils down to one of the oldest sayings in computing: garbage in, garbage out. If your data is biased, or just plain wrong, then the model you train on it is going to be biased and wrong too. It's as simple as that. The predictions it makes will reflect the flaws in its education. All right, we've covered the basics of translation. We know about the pitfalls of bad data. Now it's time for a power-up. We're going to look at an advanced technique that lets our models grasp much more complex, nonlinear relationships. This technique is called a feature cross. And really, it's all about combining two or more features to create a brand new synthetic one. This is the secret to helping simpler models understand how different things interact with each other in the real world. Let's take a simple example with leaves. Say you have one feature, edges, which can be either smooth or toothed. And you have a second feature, arrangement, which is either opposite or alternate. Now, each of those is useful on its own. But what if we create a feature cross? We can make a new feature called, say, toothed opposite. Suddenly, the model isn't just seeing two separate facts, it's seeing a combined, more powerful concept. Let's go back to our translator metaphor. One-hot encoding is like giving our model a dictionary of individual words. But feature crosses? That's like teaching it grammar. It's how we combine those words to create new concepts and understand more nuanced ideas that just aren't there when you look at the individual pieces alone. At the end of the day, our models are only as smart as the data we give them. They're literally a reflection of how we translate our world for them. And that leaves us with a really big question, doesn't it? As we get better and better at this, what important human context, what subtle truths about our world are we still failing to translate? What are we leaving out of the conversation?